Thank you to the organization for letting me present my thesis today and create such an important international space to talk about BIM. And thanks to all participants for being here today. I would like to start introducing myself a little bit. I'm Cristian Rincon. I'm from Colombia. As you can see here, it's still in the night. And civil engineer with around 8 years of experience in geotechnics and project management. Last year, I got a master degree in building information modeling from the European Master BIM Plus with the thesis entitled Geotechnical BIM for Quantity Takeoff in Tunnel Structures with Ground Deformation. And currently, I am BIM consultant for Latin America and Deutsche Bank. So let's start with a brief introduction. The scope of the thesis was developed in four main sections. First, geotechnical information modeling, bibliographical research regarding the state of the art of BIM for geotechnical analysis in tunneling projects. Next, BIM to finite element analysis, practical software exploration to define workflows to integrate geotechnical BIM models with ground deformation analysis in tunnels to be excavated following the new Austrian tunneling method. Then, quantity takeoff in tunneling structures. A practical test by a study case to define workflows for the quantity takeoff considering ground deformation. And finally, a study case that I will quickly show the results on the project second track the Basha Copper. Okay, so just a little bit of context so everybody knows what I will be talking about the next 10 minutes. The thesis was focused on the new Austrian tunneling method that consists in a mechanical excavation by several sequential steps, followed by the supports. Okay, now what is the challenge to address? The tunnel design section is defined by the geometric design of the road, the railway, or whatever it is for the tunnel. So the design section must correspond to the excavation deformed line. This means that a theoretical excavation line must be considered in order to get the design section after the deformation occurs during the excavation. This also means that excavation volumes and shotcrete quantities are directly related to the geotechnical analysis to estimate this ground deformation. Okay, let's start talking about geotechnical BIM. So, what is geotechnical information modeling? So a possible definition for this is the set of digital tools, processes, and standards for the collaborative management of surface and subsurface data during the asset life cycle. As you may know, there is a huge potential and advantage of processing geotechnical and geological surveys in a 3D environment. As you can see here, traditionally we tend to create geotechnical or geological cross-section by the projection of boreholes or any type of survey in a section plane. Nowadays, there are interesting tools that allow us to create 3D models by analyzing different types of sources of information. One of those tools is Leapfrog, a tool that allows us to produce a very complex geological 3D models, integrating different sources of information as borehole data, maps and images from GIS data, geological structural data, and topography from a dam, a point cloud, surface files, and among others. This tool has very good interoperability capabilities with other tools as Civil 3D, where the model could be also edited. Okay, now let's see how we can integrate these geotechnical BIM models with a finite element analysis. So here the foundation is how finite element analysis software are developed. Every single FEA software has three basic models. The preprocessor, that is an user interface where the model, either 2D or 3D, is created and translated into a mesh. Then we have the processor, that is the core of the software, where the mesh is read as a matrix and is calculated and solved. And then the post-processor that's again an interface that allows us to read the calculation results in a graphic environment. So what is the proposal here? It's quite simple, just to use BIM tools as a preprocessor in order to use geotechnical BIM models as part of the analysis workflow. So just due to the time, I will just say that I test these workflows with several tools as RS3, Flag 3D, either Plaxis, for 2D and 3D analysis. Okay, now let's talk about the quantity takeoff. So first of all, there's a brief general workflow for the quantity takeoff in the context of the tunnel and structures. So the client has defined the WBS and we got the models from designers. Then as an estimator, we create selection sets based on the properties within the BIM models using a proper tool. In this case, I use a Vexel Manager to keep working in an open BIM format basis, which is very important infrastructure for the asset management later. After this, I just create a BOQ from the selection sets. But what is very important here to keep in mind is that the WBS definition is key. So as I mentioned, selections are done from properties, but now what is the problem? As you can see here, many objects are classified as building element proxy just because of the lack of definition in the IFC schema for tunneling structures. It means tunneling models must be prepared carefully with property set that allows to identify each element according to the project WBS. Also, of course, for quantity takeoff, the properties related to quantities must be in the object considering the pay items defined in the WBS. So again, you can see the WBS is very important to classify and prepare BIM models accordingly. And please take into account for infrastructure, the WBS may change in each project, so it's not so standardized as it is for buildings. Okay, let's go back to the ground deformation. What we can see here is a simplified representation of how a tunnel cross-section should look like in a BIM model. So starting from the middle, we have the design cross-section. After that, we have the inner lining, the concrete support, and then the waterproof isolation. But then after that, we have a void there that is very important. And after this void, we have the shotcrete, and that finally represents the so-called theoretical excavation line. So what is for that void? So actually, is the best way to represent the ground deformation in a BIM model for quantity takeoff. So that will be the difference between a quantity takeoff BIM model and an as-built model for a tunnel. Because in fact, this representation won't happen in the real life during the construction. But in real life, after the excavation and the shotcrete, the deformation will happen, and then we cast the inner concrete, so there's no void in real. But this is a representation of two conditions in different points in time in the same model in order to measure the correct excavation at the shotcrete quantities. So now talking about the quantity takeoff, here is an example of a tunnel excavation BIM model where we can see that the volume reported by the designer and the actual volume of the object has a difference of 6%. Someone could think 6% is not significant, but in 20 kilometers, believe me, it's quite important. So why is that difference? So I have here an example of 1 meter of excavation step line that is easy to recognize that the designer calculate the volume by the product of the cross-section area and the step length. But at first, this looks like it makes sense, but it's not because of the vertical and horizontal curves in the tunnel alignment. So the step length is 1 meter only in the middle point of the cross section. So in order to have accurate volumes in this case, it's better to use the native volume calculation of the tools. So most of BIM tools calculate the volumes by the discrete elements that represent the solid. So I mean the mesh elements, uh, as you can see in the bottom of the slide. Okay, so finally, let me introduce very shortly the project I use as a study case to develop my thesis. And at this point, I should mention the project was provided by the company Geoportal from Slovenia, which I'm very grateful for. So, very short description. The project is a second railway track that connects Tibasha with Koper in Slovenia with a total length of 27 kilometers, 20 kilometers of which consist in tunnels. So for this project, I did a quantity takeoff review for the excavation and shot with volumes in tunnels 4 and 8, where I found a difference from 10 to 60% between the calculated quantity and the value reported in the BOQ. So I'm very glad to say that the designer take this into consideration to check again the complete BOQ and improve it. At last, as I was working with the excavation model and the geotechnical model of the project, I did notice the tunnel was indeed just a small line in the middle of a huge geological model. So it was not easy to understand really the geology along the excavation of the tunnel. So because of it, I propose to have an intersection model of it. So an excavated geological build model, if you want. This model can be used as a single source of geological and geotechnical information during the excavation phase of the project, as you can see here. Okay, so let me summarize some conclusions. So first, geological and geotechnical tools improve the accuracy in 3D representation and facilitates the information management, but further standardization is needed. It is possible to integrate finite element analysis tool with BIM tools, and in this field, there are huge possibilities to improve or automatize this interpretability using Python, just as an example. Regarding the quantity takeoff in tunnels, it's very important to define, since the BIP, properties according to the WBS of the project, and also still more specific guidelines to standards are required. About the study case, we could notice how important it is to define the measuring techniques for the quantity in such a big project. And finally, I would like to encourage people to test using geological excavation models as a tool to manage information during the excavation. So just some references. And okay, so thank you all for the time. Muchas gracias. And of course, thanks to BIM Plus Master, and once again, thanks to GeoPortal.